Welcome back to Lesson 8, Unit 1, the overview of our course, Networks and Distributed Systems. In the last lesson, we were talking about ISPs, both access ISPs, regional ISPs, and Tier 1 ISPs, and a couple of other connections. So let's proceed where we left off. As a packet travels from one node to the next node along its path, the packet suffers from several types of delays at each node along the way. The most important of these delays are nodal processing delays, queuing delays, transmission delays, and propagation delays. Together, these delays accumulate to give a total nodal delay. The performance of many internet applications such as research, web browsing, email, maps, instant messages, voice over IP, and so on are greatly affected by network delays. As part of its end-to-end route between source and destination, a packet is sent from the upstream node through router A to router B and so on down the line. Router A has an output link leading to router B. This link is preceded by a queue or a buffer. When the packet arrives at router A from the upstream node, router A examines the packet's header to determine the appropriate outbound link for the packet and then directs the packet to this link. You remember our discussion about routing? It determines the appropriate outbound link by examining the forwarding table. In this example, the outbound link for the packet is the one that leads to router B. A packet is transmitted on a link only if there is no other packet currently being transmitted on the link and if there are no other packets preceding it in a queue. If the link is currently busy or if there are other packets already in the queue, the newly arriving packet will then join the queue. The time required to examine the packet's header and determine where to direct the packet is part of the processing delay. The processing delay can also include other factors, such as the time needed to check the bit level errors in the packet that occurred in transmitting the packet's bit from the upstream node to the router. Processing delays in high-speed routers are typically on the order of microseconds or less. At the queue, the packet experiences a queuing delay as it waits to be transmitted onto the link. The length of the queuing delay of a packet will depend on the number of earlier arriving packets that are queued and waiting for transmission on the link. If the queue is empty, then the packet's queuing delay will be 0. On the other hand, if the traffic is heavy and many other packets are also waiting to be transmitted, the queuing delay will be long. The time it takes to push the packet from the queue or buffer onto the link is referred to as transmission time. This time is calculated as the number of bits in a packet divided by the rate at which they can be transmitted. Once a bit is pushed into the link, it needs to propagate to router B. The time required to propagate from the beginning of the link to router B at the end of the link is propagation delay. The bit propagates at the propagation speed of the link. The propagation speed depends on the physical medium of the link, that is, whether it's fiber optic or twisted pair or whatever. Unlike the other three delays, processing, transmission, and propagation, the queuing delay can vary from packet to packet. For example, if 10 packets arrived at an empty link at the same time, the first packet transmitted will suffer no queuing delay at all, while the last packet transmitted will suffer relatively large queuing delay. Therefore, when characterizing queuing delay, one typically uses statistical measures such as the average queuing delay, the variance of queuing delay, and the probability that the queuing delay exceeds some specific value. So far, we've talked about the delay at a single router. Now let's examine the total delay from source to destination. To understand this concept, suppose that there are n-1 routers between the source host and the destination host. Let's also suppose that the network is uncongested, so that queuing delays are negligible. The processing delay, the transmission delay, and the propagation delay on each link accumulate to give an end-to-end delay. To see evidence of end-to-end delay in a computer network, we can make use of the traceroute program. Traceroute is a simple program that can run on any internet host. When the host specifies a destination host name, the program in the source host sends multiple packets toward that destination. As these packets work their way through the network toward the destination, they pass through a series of routers. When a router receives one of these special packets, it sends back to the host a short message that contains the name, address of the router, along with information about the time taken. Different operating systems have different names for the traceroute utility. Why don't we take a look at one of them? Now I've made my way to the command prompt, the command line interface of my computer, which is a Windows 10 computer. If you have a Windows 10 computer, you can choose CMD at the run button and get to this line. And I'm going to input the traceroute command used by Windows. It's TRACERT. And then I'm going to input the host that I want to trace route to, which will be sprint.com. Now you are seeing routers respond to my request. All right. There you go. There's quite a few routers between my computer and Sprint. You notice the delay right there? All right, finally got a response. It's taking longer and longer the closer I get to Sprint from each router. Now I don't know how many routers there are between me and host, so I'm going to stop this thing with a Control-C and exit and get back to our lecture. Now here you see the graphic showing us going through there, and this is a graphic that shows a typical response from a traceroute command. We have assumed that the router buffer can hold an infinite number of packets. Actually, the capacity at the buffer will vary depending upon the router design and cost. So if a packet arrives at a full queue, the router will drop the packet. What we need to understand is that the communication between the devices is going on. When that packet was sent, the sending host started a timer and waited. Once the packet is received at the destination host responds with an acknowledgement. If that source host timer goes off before the acknowledgement is received, the sending host assumes the packet was lost. From the sending host point of view, the packet loss looks like the packet was sent but never received. The number of lost packets increases as the network traffic increases. Therefore, performance at a node is often measured not only in terms of delay, but also in terms of probability of packet loss. Soon we will see that a lost packet may be retransmitted in order to ensure that all data are eventually transferred from the source to the destination. Well, that's enough for this lesson. Let's take a break. Go take care of any assignments that you have, and when you're ready to start again, come on back for lesson 9.